So dear students, welcome to the second lecture on classical mechanics. So in the very first lecture we had discussed some fundamental ideas related to mechanics in general, and we have seen that the basis of all the mechanics was Newton's laws of motion, which had its own limitations. So it was alternately developed by or improved by the concepts given by Lagrange, Hamilton and many others, which is nowadays known to be as classical mechanics. And we have discussed that whatever be the type of mechanics that we discuss, basically we are dealing with something what is known as equations of motion, which will help us to make predictions regarding the future trajectory of mechanical systems, dynamical systems, based on the knowledge of initial conditions. So the backbone of every branch of mechanics is some sort of an equation of motion. In the case of Newtonian mechanics, of course you know, one of the powerful branches we have seen and used so far has got the three laws of motion given by Newton as the foundation. Similarly, every new branch of classical mechanics that we are yet to discuss, namely the Lagrangian mechanics and the Hamilton mechanics or the Hamilton-Jacobi mechanics, all these approaches, otherwise known as formalisms, are having its own equation of motion. So in the coming lectures we will be getting familiarized ourselves with the different equations of motion in each of these branches of mechanics or approaches of mechanics, and we will compare the advantages or the limitations of each of this method, because no method is complete by itself. Every method has got its own pitfalls or its own limitations, so we go after the other improved mechanics. And as I told you in the foundation lecture, that the classical mechanics has also got some limitations. Basically, the laws of classical mechanics were devised to explain the macroscopic world, and it was found that when we try to understand the microscopic world in detail, the laws of classical mechanics becomes insufficient, which has to be modified, and that gave birth to the new branch of mechanics, what is known as quantum mechanics. So even though classical mechanics is insufficient in discussing the microscopic world completely, we will see that there is some advantages of learning classical mechanics still. So maybe we have a genuine doubt in our minds if we say that the classical mechanics is so old and it is redundant. Why do we always have, or why a student of physics is always forced to have a study of classical mechanics even in the postgraduate classes? The reason is well and clear. Because the classical mechanics or the principles of classical mechanics or its approach can be actually generalized to learn what is known as quantum mechanics. Or we will see that the concepts that we are using or the techniques that we are using in quantum mechanics will have a strong foundation on the laws of classical mechanics. So only the approach is different, but the concepts are actually solidified when you learn classical mechanics. So that is one of the relevance of learning classical mechanics. So we can say that even though most of the modern day problems are or can be solved by using quantum mechanical systems or quantum mechanical assumptions, still we are in need of classical mechanics principles. We have to master those principles so that we can have a very comfortable transition to the world of quantum mechanics. Okay. Now another relevance is that quantum mechanics requires a number of formulations, mathematical formulations and mathematical techniques are needed, and the logic behind or the motivation behind all these different mathematical techniques. For example, you have learned about certain type of bracket formulation in quantum mechanics, like you have learned about the commutator bracket relationships between position and momentum and many other dynamical variables. You have learned that there are a number of commutator bracket relationships in quantum mechanics. Okay, whether two operators are commuting or not, commuting operators or not, commuting or non-commuting operators, and you'll be able to make a lot of predictions regarding the nature of the dynamical variables corresponding to those operators based on the commutational relationship between those two variables. Okay, so from where do we get the concept of commutation brackets? Actually, we'll see that the concept of commutation brackets in quantum mechanics has been just an extension of another type of bracket relationship in classical mechanics, which is named as the Poisson bracket. So we'll see that the commutator bracket in quantum mechanics is actually just an advanced form of, or it's an alternate form of the very old say mathematical technique of calculating the Poisson bracket of two dynamical variables, and just by introducing minor modifications in the Poisson bracket formulation, you are able to just directly jump into what is known as the commutator bracket formulations. Not only that, there are several other mathematical techniques, several other mathematical methods that is used in the advanced formulations of quantum mechanics. They all have its motivation from the techniques that we have just mastered in classical mechanics. So that is yet another relevance of learning classical mechanics. Classical mechanics helps us to master the different or various mathematical techniques that is required for understanding the advanced formulations in quantum mechanics, and we will see which all techniques are having corresponding things in quantum mechanics and also. Okay, so this is a broad idea regarding what is the relevance of learning classical mechanics still when in the era of quantum mechanics. And we'll see that the ideas of phase space, the idea of phase space that you have familiarized in your stat mech classes. Actually, the idea of phase space is discussed in detail in the discussion of classical mechanical concepts. Because when we start with what is known as the Hamiltonian dynamics, we will see that the Hamiltonian dynamics is developed in a abstract mathematical space known as phase space. And actually it is the Hamiltonian mechanics which is directly related to the quantum mechanics, where the concept in when you with your first experience of quantum mechanics in undergraduate courses, maybe in your sixth semester, you have seen that a system is described by what is known as Hamiltonian. Okay, in quantum mechanics, a system can be described, or all the information regarding a system can be obtained by knowing its Hamiltonian. Okay, which represents in many cases Hamiltonian of the system represents the total energy of the system. Not always, okay, need not be always. We will see that in our detailed discussion in the coming modules. So the Hamiltonian approach, okay, actually is getting or giving new concepts such as that of the Hamiltonian. The Hamilton's approach in classical mechanics actually gives rise to the very core concept of Hamiltonian in quantum mechanics. The only difference is that those dynamical variables of interest in classical mechanics will be treated as some sort of operators when you go to quantum mechanics. So that is the operator formalism. And that is a major difference between classical mechanics and quantum mechanics. In quantum mechanics, most of the dynamical variables are given a status of that of a mathematical operator, because it is based on some sound postulates which treats these dynamical variables as operators, and these operators are operating on certain eigenfunctions to give you an eigenvalue. All those are the techniques that you have learned in quantum mechanics. Okay, so the ideas, the basic idea, this is what I want to summarize. The basic idea or the basic approach or mathematical techniques that has become the foundations of quantum mechanics has got its motivation from the concepts of classical mechanics. So it is imperative that every student of physics who want to master the modern techniques of quantum mechanics should have a sound formulation or sound you can say mastered concepts of classical mechanics. Okay, otherwise it becomes meaningless. We will have to depend too much on other things. So that is a basic idea regarding the relevance of classical mechanics. Now just let me go to the different discussion of the various branches of classical mechanics. As you have seen that the starting point is always Newtonian mechanics, and as we have seen that Newtonian mechanics is having great stress on quantities which are vectorial in nature. Okay, you know that Newtonian mechanics usually discusses quantities which are vectors like which are vectors like, you know, see, we discuss about momenta, right, momentum of particles. We discuss about the rate of change of momentum, which is defined as the force, right? Okay, so the angular momentum, all these quantities that we usually come across in our Newtonian mechanics are basically vectors. So they are basically vectors, and vectors, or using vectors to describe the mechanical system, has got its own advantages and its own mathematical limitations. Okay, so for example, if you are using vectors, you know, you will be able to just include more information regarding a physical quantity. Like, you know that now in speed you have some information regarding the rate of motion of the object, but in velocity you have more information regarding rate of motion of the object, because it along with the magnitude of the rate of change, it gives you the direction along which this rate of change is happening. So that is one of the advantage of using vectors, you know, and that is why we were forced to use vectors, especially when we are dealing with the three-dimensional motion. We are bound to know, okay, the vector nature of all these physical quantities. But along with the vectorial approach, or along with the advantages of this vectorial method followed in Newtonian mechanics, there are some associated limitations as well, because if you are learning, or if you are trying to analyze a very complicated connected body problems and all, many times sorting out the vector, sorting out the direction of different forces or different vectors in that problem becomes a tedious process. We cannot say it is it's impossible, but it becomes a tedious, very time consuming process. Okay, you have to find out in which direction one force is acting, in which other direction one tension is acting, and you have to find out the resultant force, because basically Newtonian approach is centered around applying the second law of motion, right? You know, F equal to ma, and F in this equation always denotes the net force acting on the system. So many times you have to we are forced to find out the net or the resultant force acting on the system under question. And finding the resultant force means you should know both the magnitude as well as direction of all the individual forces that is acting on the system. If you do not know, or if you are not able to clearly point out both the magnitude as well as the direction of all the forces acting on a system, the knowledge about the system will remain incomplete, and you won't be able to apply Newton's law of motion, because Newton's law of motion always relates the net force acting on the system. So you're supposed to know the resultant force. Okay, so which makes in very complicated problems involving many body problems, especially that of something like n body problem in rigid body dynamics and all, it becomes a bit tedious process. So advantage as well as disadvantage exists for every approach. We try to overcome the limitations, okay, of the vectorial technique or the vectorial approach of Newtonian mechanics by introducing another set of mechanics, what is known as analytical mechanics. So remember, the analytical mechanics is actually an improvement, or it is an alternative formalism. Alternative means a formalism which is derived its motivation from the existing one, but its method is a bit different, that's all. Okay, so it's an alternative but equivalent. This is always remember. You remember that most of the mechanics, most of the discussions of Lagrangian mechanics or Hamiltonian mechanics, its roots will be in Newtonian mechanics itself. Most of the equations also will be, equation of motion will be also derived from the Newtonian equation of motion, even though it can be derived by other methods like principle of action and all. So so remember that all these different approaches are considered to be equivalent formalisms. So maybe this is another word that will be coming across in your literature, in textbooks and all. Newtonian formalism, Lagrangian formalism, Hamiltonian formalism. Formalism means it's a approach which are equivalent to each other. So it's an equivalent formalism, always remember. So the core difference between the Newtonian mechanics and the analytical mechanics is that Newtonian mechanics is basically vectorial in its approach. This is the core difference. Basically, it is vectorial in its approach, because the fundamental concepts of Newtonian mechanics are force, momentum, etc., which are vector in nature. So analyzing the magnitude as well as direction of these vectors involved in complicated dynamical problems becomes a tedious process. So it has got its own limitations. Okay, so in order to overcome that, in analytical mechanics, you will see that it's instead of a vectorial approach, analytical mechanics has got a scalar approach. It's a scalar approach. Scalar approach in the sense that you will see the central concepts of all analytical mechanics will be some sort of scalars. For example, energy is one of the core concept. Even though say like force is the core idea, or force is a central theme, I can say. Force is the central theme. Force is the central character or central theme or character, I can say. In Newtonian formulation, energy is the central character. Energy is the central character in the analytical mechanics branch of view. Okay. So, but this energy, it's not directly the energy. So, energy has got diverse forms. What type of energy? It depends on the energy. Okay, in some cases, it is the difference between its kinetic and potential energy. So, in some cases, in some formalisms like a Lagrangian formalism, we define a function known as the Lagrangian of the system, which is defined as the difference between its kinetic energy and the potential energy. Okay, so here Lagrangian is an energy, it's a function, difference between the kinetic and potential energy of the system. Okay, whereas in Hamiltonian approach for conservative systems, you will see that it is defined as T plus V. Remember, I just say there are some conditions for everything. You will see that Hamiltonian the system represents the total energy of the system for what is known as conservative systems. In conservative cases, it is the thing. So you can see that both Lagrangian and Hamiltonian, which becomes a central theme in the Lagrange's mechanics and the Hamiltonian mechanics, both are energy, some sort of energy functions. So, energy is a scalar. So, that is the major difference between the Newtonian mechanics and the analytical mechanics. So, the Newtonian mechanics is basically a vectorial approach, whereas the analytical mechanics is basically a scalar approach. And the scalar approach, along with its limitation, it gives you some more advantages also, some mathematical advantages also. What is mathematical advantage? You need not worry about. You need not worry about the directions of the quantities involved in analyzing a very complicated problem. You need to just calculate the total energy or some proper well-behaved energy function like Lagrangian of the system or the Hamiltonian system. Once you calculate the Lagrangian of the system or the Hamiltonian of the system, which are two defined functions, we will see in detail all these functions in the coming lectures. So you will see that you will be able to use the Lagrange's equation of motion or the Hamiltonian equation of motion. You substitute these quantities in the proper equation of motion and you solve for that equation. You will be directly able to get whatever information you needed regarding the particular system in question. So that is what makes the analytical mechanics different from the Newtonian mechanics, right? So by our focus of the paper classical mechanics in your first year or first semester postgraduate course will be analytical mechanics. So we will be discussing in detail the method of Lagrangian mechanics, the method of Hamiltonian mechanics, the method of Hamilton-Jacobi mechanics. So these three are the three fundamental analytical mechanical systems that we are going to discuss in the coming modules. And we will solve some standard problems by using each of these mechanical branches, right? So before we move on to the ideas of analytical mechanics, okay, so always remember this Lagrangian mechanics, Hamiltonian mechanics, Hamilton-Jacobi mechanics, all these things are collectively known as what is known as analytical mechanics, right? So these are the analytical mechanics, right? That's why I told you that when you just search in the net for some textbooks or some reference material for Lagrangian mechanics, you may find the textbooks with the name analytical mechanics. Analytical mechanics means mostly it is discussing Lagrangian or Hamiltonian mechanics, right? So before we discuss the basic ideas of Lagrangian and Hamiltonian mechanics, I think it will be useful to discuss some standard problems. Which you might have done in your lower classes, maybe in undergraduate classes or your secondary or senior secondary classes, by using the Newtonian approach. Okay, so that you will get an essence of what is the difference. When later we will solve the same problem by using Lagrangian mechanics and Hamiltonian mechanics. So you will be able to understand clearly that what difference it is, okay, what type of differences it can give, which method is easy or which method is difficult. You will have a taste of that. Okay, so in order to do that, I'm trying to take up 1 or 2 problems, very common problems, standard problems in Newtonian, which can be solved by using Newtonian mechanics, and later we will see how it can be solved by using the analytical approaches, right? So that's about this particular video. So I'm trying to make the videos of short duration due to several reasons. One reason is that you can take a break between the videos, okay, without losing the continuity. Of course, you can pause and see the videos, but it's always found that okay, to be easier, okay, if you can just stay focused on to different okay, short videos. So at the most, I'm trying to limit my videos to some half an hour. So we will have a larger number of videos. I will, for sake of accessing it easily, I will just name these videos as lectures, but maybe 2 or 3 lectures will form one complete class. So I will be naming this lecture as lecture number 2, and maybe you will have to listen on the same day, or you'll have to watch on the same day lecture 2, 3, 4, like that. Okay, so I'll give the messages in your WhatsApp group, so that you can just have continuity. So always remember, do not miss the lectures in between. Try to follow the serial number of lectures so that you follow the continuity in our discussions. Okay, so we will discuss 2 standard problems in the next lecture. For the time being, just bye. Thank you.